Good morning, students. Myself, G. Shankar from EC Department, Spectral Engineering College. So today we are going to discuss about the energy density spectrum and the power density spectrum. Energy and power density spectrum. In that energy density spectrum, energy spectral density, and power density spectrum, power spectral density. Energy spectral density denoted as psi of omega or psi of f, and power density spectrum, the power spectral density denoted as S of F. Okay. You can see in the last class we already discussed about the energy density spectrum. Again, I will explain brief for the energy density spectrum and energy spectral density. A spectral density, it is a distribution of energy or power of a signal per unit bandwidth as a function of frequency. Spectral density means either it is energy, it is a distribution of energy or power of a signal per unit bandwidth as a function of frequency. Energy signals, what is energy signal means? A signal with finite energy and zero average power. Finite energy and zero average power. Finite energy means 0 less than E less than infinite, and power is equal to 0 are called energy signals. A signal with finite energy and zero power. Finite means it is in between of the 0 to infinite, not equal to the 0, not equal to the infinite, in between. The normalized energy, or simply energy of the signal x of t, is defined as the E is equal to integral minus infinite to infinite, the squared magnitude of x of t dt. The energy of a signal exists only if E is finite, that is, if 0 less than E less than infinite. Okay, my dear students. So, to get it is a spectral density, energy spectral density, psi of F is equal to the squared magnitude in terms of the frequency. Spectral density is always in the frequency, my dear students. It's a function of frequency. It is distribution of energy or a power of a signal per unit bandwidth as a function of frequency. As we know, the Parseval's theorem of energy signals, E is equal to integral minus infinite to infinite, squared magnitude of x of t dt, and 1 by 2 pi integral minus infinite to infinite, the squared magnitude of x of omega d omega, or it is also equal to the squared magnitude of x of f into df. Because the d omega is equal to 2 pi f. Omega is equal to 2 pi f. Apply the derivative on both sides. D omega is equal to 2 pi into df. Okay, and here the 2 pi and the 2 pi get cancelled, convert into the normal frequency. Okay, x of t is equal to x of omega, and x star of t is equal to x star of minus omega. Okay, conjugate of x of t such that x star of t is a Fourier transformation is x star of minus omega. Okay. Now the squared magnitude of x of t is equal to x of t and x star of t, and substitute the x star of t is a inverse Fourier transformation definition. X of t is equal to, not the x star of t, x of t is equal to inverse Fourier transformation definition, and check that x of omega integral minus infinite to infinite x of omega and e power j omega t and d omega and the dt. Interchange the integrations, x of omega and x star here and e power plus j omega and dt, as this function is a x of omega actually, but here the substituting of omega as minus omega, and keep the signal is a conjugate signal x star of omega. Okay, my dear students. Change of omega here the minus, and the signal given is a star conjugate signal x of t. x of omega and x star of omega into d omega is equal to 1 by 2 pi. If the x of t and x star of t is the squared magnitude of x of t, and x of omega and x star of minus omega is also squared magnitude of x of omega into d omega. Because we are taking the magnitude, so no need of taking here the minus values. Omega is equal to 2 pi f, the d omega is equal to 2 pi f into df. E is equal to the integral minus infinity infinite x of f squared magnitude of x of f into df. This is called Parseval's theorem for energy signals, also called as Rayleigh's energy theorem. Okay, yesterday we already discussed this one. Now coming to the energy spectral density. Energy spectral density. The energy spectral density means spectral density is nothing but the distribution of energy or a power. The energy or a power for a bandwidth of a function of a frequency. So energy spectral density function gives the distribution of energy signal in the frequency domain. Distribution of energy of the signal in frequency domain. Okay, for an energy signal, the total area under the spectral density curve. So whenever if you take the integral of minus infinite to infinite, the signal is a area under the curve. We know we already discussed in the, not in the discussion, RVS with the EC students will well known that the area under the curve, the integral minus infinite to infinite delta of t dt is equal to 1. Okay. The total area under the spectral density curve plotted as a function of a frequency is equal to total energy of the signal. Total energy of the signal. It is also called as energy density spectrum or ESD, energy spectral density. It is a designated by the psi of f is given as psi of f is equal to squared magnitude of x of omega. Squared magnitude of x of omega is a frequency. For an energy signal, the total area under the spectral density curve plotted as a function of frequency is equal to the total energy of the signal. It is also called as energy spectrum density spectrum or energy spectral density. So both are the same, energy spectral density or energy density spectrum. The proof here, let x of t and y of t be the input and output respectively of a linear system. Let x of t, Fourier transformation x of omega, y of t, the Fourier transformation is y of omega, and h of omega be the system transfer function. System transfer function output by the input. Output is a y, input is a x, h is equal to y by x. So y is equal to h into x. The energy spectral density of the input function, energy spectral density of the input x of t is psi x of omega is equal to psi x of omega is equal to the squared magnitude of x of omega. Psi y of omega is equal to, because it is a suffix, if I am taking the y, it is a y of omega square. Okay, and psi y of omega is a squared magnitude of x of y of omega is equal to, as the function is a y of omega is h and x, squared magnitude of h of omega and x of omega. Separate that is a squared magnitude of h of omega and a squared magnitude of x of omega. So what is the x of omega? Psi of omega. So psi y of omega and psi x of omega. Thus, the energy spectral density of the output response of a linear system is the product of the output response of a linear system is the product of the energy spectral density of input psi x of omega and square of the magnitude of the transfer function. the square of the magnitude of the transfer function h of omega square minus 2x. Energy of the output signal Ey is equal to integral minus infinite psi y of f into df. Have you got this equation, my students? According to the Parseval's theorem, saying that E is equal to integral minus infinite squared magnitude of x of t dt is equal to integral minus infinite so 1 by 2 pi also, students. Squared magnitude of x of omega into d omega is equal to integral minus infinite squared magnitude of x of f into df. Okay, so what is the squared magnitude of x of omega or the x of f? Is nothing but energy spectral density only, psi x of omega into d omega, or integral minus infinite psi x of f into df. Okay, now I am taking here, it is a psi Ey is equal to, it is also the energy signal on Ey is equal to, now suffix is changes as psi y of f into df. That is equal to 1 by 2 pi, here the 1 by 2 pi, my students. 1 by 2 pi into psi x of omega into df, d omega. And that is equal to 1 by 2 pi integral minus infinite. What is the psi y of omega is equal to the total function squared magnitude of h of omega and psi x of omega into d omega. Okay, my dear students. Now, if this is an even function, changing it as the total function is an even function, means 2 into the integral 0 to infinite. I'm taking the from minus infinite to infinite. Both are, it is an even functions. We can represent it as a 2 into integral 0 to infinite. See here, the integral is not the from minus infinite to infinite. I'm changing the 2 integral 0 to infinite. So both sides is the same. Then you can multiply the 2 minus 2 is equal to 2 to get cancelled. Here the 2 is there and here the 2 get cancelled. 1 by pi integral 0 to infinite the square magnitude of h of omega and psi x of omega into dm. Fine. If the linear time invariant system is an ideal low pass filter with the lower and upper cutoff frequencies FL and FH respectively, then what is the h of omega? FL and the FH. Let us raise the FL here and it is a FH. The linear time invariant system h of omega is equal to 1 in the range of FH and FL. Okay. So modify the above equation 1 by pi, the integral 0 to infinite now is a FL to FH. Psi x of omega into d omega, substituting of h of omega is equal to 1. Taking from here itself, the 0 to. That 0 only you can take as a FL to the FH, psi x of omega into d omega. And omega represented as a psi x of 2 pi f and the 2 pi f into df. And pi get cancelled, 2 into integral FL to FH, psi x of omega into d omega as energy. Ey is equal to 2 pi as substituting of omega is equal to 2 pi into df, 2 to get cancelled, 2 into integral FL to FH, psi x of omega, psi x of f into d omega. The omega is changes to the normal frequency. Okay. Is energy spectral density output function Ey is equal to see the total area under the spectral density curve plotted as a function of the frequency. Here the frequency energy spectral density is equal to the total energy of the signal EY is equal to. So EY is equal to 2 into FL to FH psi x of F into DF. Okay, my dear students. Coming to the properties of energy spectral density. The first property, same what we derived previously, the total area under the energy density spectrum or energy spectral density is equal to the total energy of the signal. Total energy of the signal is equal to the area under the energy density spectrum minus infinite to infinite psi f of df or 1 by 2 pi psi omega into d. And second property saying that if x of t is the input of the linear time invariant system with impulse response h of t, then the input and output of energy spectral density functions are psi y of omega is equal to squared magnitude of h of omega into psi x of omega and psi y of omega. F is equal to, it's an angular frequency and the normal frequency. And autocorrelation function is related to the energy spectral density is a Fourier transformation relation. The autocorrelation function R of tau and energy spectral density psi of omega forms a Fourier transformation pair. Forms a Fourier transformation pairs. Okay, my dear students. Now the second part is a power density spectrum or energy, not the power spectral density. What are the power signals here? Previously, energy signals means energy is finite and the power is a zero. Energy is finite and the power is a zero. Here the power signals is signal with finite average power and infinite energy. So if the power signal is a power signal, power is a finite average power. If the energy signal is energy, means energy is a finite, but power is a zero there. And for the power signal, power is a finite and energy is infinite. Energy is infinite are called power signals. Examples of the periodic signals. Since it is a periodic signal, the average power, it is defined as average power dissipated by the voltage. Forget about this one. Mathematically, P is equal to limit t tends to infinite 1 by t the integral t squared magnitude of x of t dt. Okay. The power P defined above is actually the mean square value or time average of the squared signal. Mean square value or time average of the squared signal. Mean square value means x square of t whole bar. That is the limit t tends to infinite 1 by t the integral minus infinite to infinite squared magnitude of x of t dt. We call it the Parseval's theorem. Parseval's theorem. Here the Parseval's theorem for the frequencies defines the power of a signal in terms of its Fourier series coefficients. That is, in terms of harmonic components present in the signal, mathematically it is given as P is equal to sum of n is equal to minus infinite to infinite squared magnitude of Cn square. So proof here, squared magnitude of x of t is x of t and x star of t. Substitute here 1 by t the integral minus infinite to, not the minus infinite, it's a minus t by the t by 2. X of t x star of t dt. But we have the exponential Fourier series. Remember, my dear students, I'm substituting here the x of t is an exponential Fourier series. X of t is equal to. In the exponential Fourier series, there is two equations are there. What are the two equations? One is analysis equation and the synthesis equation. Analysis equation is x of k is equal to. Synthesis equation is x of t is equal to sum of n is equal to minus infinite to infinite Cn into positive exponential e power j n omega into t. Okay, omega into t. Here the omega into t is there, my dear students. It is not visible clearly. E power j n omega into t. So actually in the Fourier series, we learn with the c suffix k and k is equal to minus infinite to infinite. But k is a variable and the n is also variable, my dear students. Okay. Substitute x of t, the analysis equation, not the analysis, my dear students, synthesis equation of the exponential Fourier series. P is equal to 1 by t, integral minus t by to the t by 2, sum of n is equal to minus infinite to infinite Cn e power j n omega t x star of t dt. Interchanging the order of the summation and the integration, sum of n is equal to minus infinite to infinite Cn 1 by t, the integral minus t by to the t by 2 x star c power j n omega into t dt. Okay, my dear students. That is equal to sum of n is equal to minus infinite to infinite Cn into this total equation you can see here 1 by t integral minus infinite to infinite x star of t e power j n omega t dt as a Cn equation. Why it is a Cn equation, my dear students? Why it is a Cn equation? Fourier series equation saying that is a coefficient of x of k is equal to as a power signal, the integral minus infinite to infinite x of t e power minus j k omega into t dt is the equation actually. Omega naught. We are saying it is omega naught, or otherwise you can use the omega. So x of k is equal to minus infinite to infinite and take the whole star x of t e power minus j k omega into t dt conjugate. Okay, my dear students. Now taking up both sides as a conjugate, x of k. Now here I am representing the Cn star. Is a Cn is equal to. So actually it is a ck, c suffix k, my dear students, because I use there it is a all the values is a k1. Now the Cn star is equal to Cn k star minus infinite to infinite. I take the star is inside x star of t and e power minus and the conjugate becomes a plus j. N value is now representing the n, k as a n, omega into t dt. Okay, my dear student. So total equation we have here x star of e power j n omega t dt, but in the power signal 1 by t integral t minus 2. Okay, as a power it becomes of total equation as a Cn star. Substituting is equal to Cn star. Sum of n is equal to minus infinite to infinite Cn star, and Cn star is the square magnitude of Cn. So power p is equal to. Actually, in the Fourier series, the Parseval theorem we derive as a p is equal to sum of n is equal to minus infinite to infinite the squared magnitude of x of k. But this x of k here we denoted as a Cn. This is a Parseval's power theorem. It states that the power of a signal is equal to sum of here the sum of square of the magnitude of various harmonics present in the discrete spectrum. Harmonics present in the discrete spectrum. Okay, so both in the energy and the power spectral density, we are using the Parseval's theorem. One is in the Fourier transformation, So one Parseval theorem is from the Fourier series equation. Power signal or power spectral density. Parseval's theorem is from the Fourier series, and energy spectral density, we are using the Parseval's theorem from the Fourier transformation. Okay, my dear friends. Now, the energy, power spectral density, PSD, the distribution of average power of a signal in the frequency domain. The distribution of average power of the signal. Previously, the distribution of energy of the signal in the frequency domain is called power spectral density or power density spectrum. All are same. To derive the power spectral density, assume a power signal as a limiting case of energy signal. A limiting case of the energy signal. Energy is included in the power itself, my dear friends. Okay. By using the energy, there is a power is generated. Consider a power signal extending to the infinite in the figure. You see the sinusoidal signal from minus infinite to infinite, and let us truncated the signal so that it is a zero outside the interval tau by 2, 0 outside the interval tau by 2, minus tau by 2 the tau by 2, it is a 0. Take the totally the tau is equal to, so x tau of t is equal to x of t, where the tau is less than the tau by 2, the magnitude of tau is, it is from the minus to the minus pi by tau by 2. Truncated power signal within the limitations plus or minus. The signal x tau of t is a finite duration tau, and hence it is energy signal with energy given by the E is equal to minus infinite x tau of t the squared magnitude. It's similar to the energy signal equation only, but here limited to the tau x tau of t, and converting into the frequency, the 1 by 2 pi the integral minus infinite to infinite x tau of omega, suffix here x tau of omega squared t omega is equal to, where the x tau of t and the x tau of omega is a Fourier transformation base. Okay. As x of t over the interval of minus tau by to the tau by 2, change this equation as minus infinite to the infinite as a minus tau by to the tau by 2, with the 1 by tau is multiplying with changing of limitations minus tau by to the tau by 2, squared magnitude of x of t into d2, and that is equal to, coming to the frequency, what is the frequency of the energy signal is a 1 by 2 pi into 1 by tau, the integral minus infinite to infinite x tau of omega squared magnitude of x of tau d omega. Okay, my dear friends. Don't confuse here. I'm changing here the minus infinite to infinite as a minus tau by to the tau by 2 with the limitations. It's the same as x tau of t over the interval of minus infinite to the infinite. So within the infinite minus infinite to infinite only, there is a finite duration minus tau by to the tau by 2. The remaining from minus infinite to the minus pi by 2 is a 0, and tau by 2 to the infinite is a 0. So within the limitations only, there is a finite duration. So I'm changing this as a minus tau by to the tau by 2 as a minus infinite to infinite with the multiplication of 1 by tau. Okay. Because 1 by t, the integral minus t by to the t by 2 is there. So P is equal to 1 by 2 pi, the power signal P is equal to 1 by 2 pi, the integral minus infinite to infinite. Limit tau tends to infinite. You see the equation the previously. Limit t tends to infinite, tau tends to infinite. Squared magnitude of x tau of omega by tau d omega. If tau tends to infinite, the squared magnitude by tau approaches a finite value. Let this finite value is denoted as S of omega. That S of omega nothing but power spectral density. Limit tau tends to infinite, the squared magnitude of X of omega by the tau. The average power of the function X of t is given as substituting this total function as X of omega in this equation. So P is equal to, or the X square of t whole bar is equal to 1 by 2 pi integral minus infinite to infinite. Substitute this function as X of omega into d omega. The normal frequency S of m f into df. Okay, my dear students. Now from the minus infinite to infinite changes as 0 to infinite to multiply the 2. Both sides is the same. 2 into 1 by 2 pi integral 0 to infinite S of omega d omega. 2 get cancelled, 1 by pi integral 0 to infinite S of omega d omega. 2 into integral 0 to infinite S of f into df. Okay, my dear students. So, for a power spectral density is a periodic function, S of omega is equal to pi into the sum of n is equal to minus infinite is the squared magnitude of Cn delta omega n minus omega, or in terms of the frequency, the input and output relations of the linear time invariant system is similar to the energy signal there. The psi y of omega is equal to squared magnitude of x of omega and s of omega, psi x of omega. Now change that as sy of omega is equal to, or sy of f is equal to. Following my students. Now the properties of the power spectral density. Here also the three properties we have. The area under the power spectral function is equal to the average power of the signal. The area under the power spectral density function, area means minus infinite to infinite, S of f into df is equal to the average power of the signal. So similar to the energy spectral density. The area under the energy spectral density function is equal to the total energy of that signal. Okay. And second, it is sy of omega is equal to squared magnitude of h of omega, s of omega. And third function, or the third property saying there is a Fourier transformation relation between the autocorrelation function and the power spectral density. R of tau is a Fourier transformation of s of omega. Okay, my dear friends. Now there is a difference between energy spectral density and power spectral density. First is, it gives the distribution of energy of a signal in frequency domain, and power spectral densities, it gives the distribution of power of a signal in frequency domain. And second point, it is given by the psi of omega is equal to squared magnitude of x of omega, and s of omega is equal to limit tau tends to infinite squared magnitude of x of omega by the tau. And third is a relation of total energy with energy spectral density, E is equal to 1 by 2 pi integral minus infinite to infinite psi of omega d omega, or in terms of the frequency, the total power is given by P is equal to 1 by 2 pi integral minus infinite to infinite s of omega into d omega, or s of f into df. Both are the same, my dear students. Here, see. But psi is energy spectral density, S is nothing but power spectral density. And fourth one, both are related to the Fourier transformation pairs of for autocorrelation function. R of tau is related to the psi of omega, R of tau is related to the S of omega. Okay, my dear students. And now the relation between of autocorrelation function and the energies or the power spectral density function. The fourth property what we are saying, or the fourth difference what we are saying in the energy spectral density and power spectral density, there is a Fourier transformation relation between the energy and the power with autocorrelation function. So what is the autocorrelation function R of tau and energy spectral density function psi of f form a Fourier transformation pair? Now see the proof. It is a very important proof, my dear students. It is autocorrelation function R of tau is equal to the two signals is a similar signals, and one signal is delayed as a received signal. One signal is delayed with the another signal, and one is a complex conjugate, or otherwise you can also take it as x of t plus tau x star of t dt. So both in the positive direction and the negative direction. Positive direction and the negative direction. Okay. So replacing now see the proof of autocorrelation function and the energy spectral density is a Fourier transformation relation. We know the autocorrelation function R of tau integral minus infinity to infinite x of t x star of t minus tau dt. Okay. Now I'm taking the x of t here, substituting the x of t minus tau, substituting the x of t minus tau by using the inverse Fourier transformation definition. 1 by 2 pi integral minus infinite to infinite x of omega e power j instead of t, here the delayed version of t minus tau d omega. Okay, so 1 by 2 pi the integral minus infinite to infinite x of t is equal into minus infinite to infinite x star of omega, because the whole star is there, x star of omega, and plus exponential value is become to the minus exponential value e power minus 0 omega t minus tau d omega. Don't put it, the d omega is a star. With respect to the omega, we're applying for the signal and the exponential values. The star, whenever you can bring it to the inside, the x star and the change of exponential plus to the minus and minus to the plus. But don't change here, it is a d omega as a minus and the star something into dt. Into changing the order and the integration, we have 1 by 2 pi, the integral minus infinite to infinite x star of omega, and integral minus infinite to infinite x of t e power minus j omega t dt, one term, and the remaining term is a minus into minus is a plus e power j omega tau into d omega. So within the parenthesis, it is our definition of the Fourier transformation. So x of omega e power j omega tau d omega. What is the x of omega and x star of omega? The squared magnitude of x of omega. So 1 by 2 pi the integral minus infinite to infinite, the squared magnitude of x of omega e power j omega tau d omega. What is the squared magnitude of x of omega? Nothing but energy spectral density psi of omega. 1 by 2 pi. 1 by 2 pi into integral minus infinite to infinite psi of omega e power j omega tau d omega. Since squared magnitude of x of omega is a psi of omega. Now you can see 1 by 2 pi x of t e power j omega t d omega is a inverse Fourier transformation of psi of omega. Okay, so therefore the psi of omega is a Fourier transformation of r of omega. F inverse is equal. So r of tau is a Fourier transformation of psi of omega. All my dear students, how we got this function? It is a very important. Coming to the relation between R of tau and the power spectral density. Power spectral density. It is also the similar Fourier transformation pair only, my dear students. Now the proof, the autocorrelation function R of tau and the power spectral density S of omega of a power signal form a Fourier transformation pair. R of tau is Fourier transformation of S of omega. The autocorrelation function of a power signal x of t in terms of the Fourier series. In terms of the Fourier series, by using synthesis equation, x of t is equal to sum of n is equal to minus infinite xn or x of k, actually here the x of k into e power j k omega naught t. Following my distance, where Cn and the C minus n are the exponential Fourier series coefficients, change as square magnitude of e power j n omega naught tau. Okay, my distance. This relation will get from the synthesis equation of the Fourier series, exponential Fourier series. Taking the Fourier transformation on both sides, we have R of tau, the Fourier transformation, the integral minus infinite to infinite, the sum of n is equal to minus infinite Cn square e power j n omega naught tau, according to the definition, e power j omega tau d tau. Interchange the orders and the summation here. The Fourier transformation of R of tau is equal to sum of n is equal to minus infinite Cn square and the integral e power minus infinite e power j tau omega minus n omega naught. These two are the bases of the same. You can add the powers by taking the j and tau is a common. One thing is a minus, we have omega, and minus into minus is a plus, we have n into omega naught d omega. Fine. Whenever there is an integration here, the integration of exponential value changes as 2 pi into delta of omega minus n into omega naught. Why it is a relation of Fourier transformation. One with the Fourier transformation, my students. It is an integral minus infinite to infinite x of t e power minus j omega t dt. Definition of Fourier transformation, x of omega is equal. Got it, my students? Now, the integral minus infinite to infinite, and now I take the x of t is a 1. Let x of t is equal to 1. What it becomes? 1 into e power minus j omega t dt. It becomes of integral minus infinite to infinite e power minus j omega t dt. Now, what is the Fourier transformation of 1? 1 with the Fourier transformation only, we get 2 pi into delta omega. Because don't substitute the minus infinite and minus infinite, becomes a 0. The 1 with the Fourier transformation is derived by using the duality property, 2 pi delta omega. But instead of omega here, omega, what is omega minus n in n omega? So change it as minus omega, you see. Instead of omega here, omega minus n omega naught into t. Okay, my dear students. So now, what is the Fourier transformation of 1? 2 pi into delta omega, but omega as omega minus n into omega naught. Okay, the Fourier transformation of 1. Here the 1 we can represent. 2 pi into delta of omega minus n into omega. And it's multiplied with the sum of n is equal to minus infinite Cn square. Okay. If it is in terms of normal frequency, there is no multiplication factor of 2 pi. Because the 2 pi get cancelled. Okay. Cn square into delta of f minus n into f naught. The RHS is a power spectral density S of omega or S of f of a periodic function of x of t. The Fourier transformation of R of tau is equal to S of omega. S of omega only. This is the equation for the S of omega, total equation, sum of n is equal to minus infinity infinite squared magnitude of Cn squared delta of F minus n into or this function. This total the S of omega, the Fourier transformation R of tau is equal. Now there is a relation of R of tau and the power spectral density is a Fourier transformation Bates. Fourier transformation Bates, my students. So we already got this equation here. See, what is the S of omega is equal to 2 pi into sum of n is equal to minus infinity infinite squared magnitude of Cn squared delta of omega minus n into omega. As a power density of a periodic signal is given by, or alternately, S of f is equal to sum of n is equal to minus infinity infinite squared magnitude of Cn delta of f minus n into f naught. This is the equation, my students. I substitute this total equation as S of omega. Okay. In this, the total function is a S of omega, or in terms of the normal frequency, Fourier transformation of R of tau is equal to S of omega. Therefore, the R of tau autocorrelation function have a Fourier transformation relation to the power spectral density S of omega or S of f. Okay, my dear students. And now the relation between the convolution and the correlation. Relation between the convolution and correlation. It is a very important. Without knowing the convolution, we don't know anything about the correlation. Now, what is the relation is there? The correlation equation for the cross correlation R12 of tau is equal to integral minus infinity infinite. Actually, the x1 of t and x2 of t. One signal is delayed with another signal. So, with the delay of tau dt, we multiplied x1 of t with the function x2 of t displaced by the tau seconds. It's not the displacement, delayed by. It is not the displaced, delayed by the, you can understand. Delayed, we can write it is displayed as a delayed by tau seconds. The area under the product curve is a cross correlation between x1 of t and x2 of t at the tau. On the other hand, the convolution of x1 of t and x2 of t at t is equal to tau obtained by folding x2 of t backward about the vertical axis at the origin and taking the area under the product of curve x1 of t and the folded version of x2 of minus t. x2 of minus t is a folded version and delayed by the or displaced by the tau. Therefore, follows that the cross correlation x1 of t and x2 of t is same as the convolution of x1 of t and x2 of minus t. When the relation between of convolution and correlation will get, the two signals x1 of t and x2 of t is similar to the cross correlation of convolution of x1 of t and x2 of minus t, the folded version of the signal. Okay, the same conclusion can be arrived at the analytically as follows. See here, the convolution of x1 of t and the x2 of minus t, my dear students. The convolution of x1 of t and x2 of minus t is integral minus infinity infinite x1 of tau x2 of, what is the formula we have the convolution? The convolution y of t is equal to x1 of t with the convolution of x2 of t. The actual formula of the convolution, integral minus infinity infinite. The first one, if I am taking x1 of tau x2 of t minus tau d tau. Now here I am taking that as a x1 of t is a normal signal and x2 of t is a folded signal. x2 of minus t. So what is the convolution now? The integral minus infinity infinite x1 of tau, x2 of, it is a minus of t minus tau d tau. What is the minus of t minus tau d tau? Integral minus infinity infinite x1 of tau, x2 of, multiply that minus with this one, tau minus t d tau. That is the same thing. x1 of tau, x2 of tau minus t d tau. Is a folded version of the second signal. Okay. Now replacing the dummy variable tau as the above integral with the another variable as a n. Wherever the tau is there, you can replace the n. x1 of n, x2 of n minus t dn. Changing the variable from t to tau here in the left hand side. x1 of tau, convolution with x2 of minus tau, and integral minus infinite infinite x1 of n, x2 of n, and the t now it becomes of the tau. Okay, so see this equation is related to the convolution or not the convolution, cross correlation. x1 of t, x2 of t minus tau dt. T minus tau dt. What is the t here? N variable, and the tau is the same. Instead of t, here the n. Instead of t, here the n. Instead of t, here also the n. This is a dummy variable. So x1 of tau, the convolution with the x2 of minus tau is equal to the cross correlation function. So cross correlation R12 of tau is equal to x1 of tau with the convolution of x2 of minus tau at the t is equal to tau. R21 of tau, the 21 of tau also, second signal is there and the first signal is a delayed. At t is equal to tau, and here also the t is equal to tau. Similarly, all of the techniques used to evaluate the convolution of two functions, convolution of the two functions can be directly applied in order to find the correlation of the two functions. Similarly, all the results derived for the convolution also apply to the correlation. If one of the function is an even function of t and x2 of t is an even function of t, x2 of t is equal to x2 of minus t, then the cross correlation and the convolution is all equivalent. Change of the second signal or the first signal is a folded version. Then the autocorrelation, not the autocorrelation, sorry, cross correlation is equal to the convolution. The relation between convolution and correlation. Okay, my dear students, x2 of t is equal to x2 of minus t, changes of. Then the cross correlation and the convolution are equivalent. Simply saying the x1 of t, the correlation function of x2 of t is changes as x2 of minus t is equal to R12 of tau. Okay, my dear friends. Next. So with this, completed the fourth unit also. Fourth unit, second part, my dear students. Fourth unit, first part of for EC students and second part of the triple students. The relation between the convolution and the correlation. So what we discussed in today's class, my dear students, energy signals, power signals, energy spectrum density or energy spectral density and their properties, and the difference between of energy spectral density and power spectral density, and the relation between of autocorrelation function and the energy spectral density, and relation between of autocorrelation function and the power spectral density, And finally, the relation between of a convolution and correlation function. Okay, my dear students. So with this, the completion of the fourth unit theoretical part. Fourth unit theoretical part. Some of the examples we have. Some of the examples is there. Let me go for the examples in the tomorrow's class. In the tomorrow's class, my dear students. So totally it's a theory part only. Theory and the derivations. Theory and the derivations. Especially this fourth unit. Second part, first part and the second parts depends upon the branches. Totally it is a theory and derivation. Theory and derivations and or otherwise some of the proofs and some of the properties we have. Yesterday also I already told that first time it is very difficult to understand. First time it is very difficult to understand when you are listening in a video class. Okay, my dear students. 2-3 times you have to listen with the same link, my dear students, and you have to write down. The 2-3 times the properties and the relations, and also the theoretical part of the convolution, the correlation. That is also the 2-3 times you have to write down. You have to practice. Then you'll get one idea. I'm not saying it is understood. After that also it is not fully understood by the students, but this practice is very important. Not only this unit, the remaining units also, always you have to go for the practice. Without the practice, it is somewhat difficult to get out into from this subject in the external point of view or into the midterm exams also. But be practice all the mathematical subjects. So especially compared to the remaining units, what we discussed previously, the first, second, and the third, and a half part in the fourth units, there is mostly the equations you have to remember, and you can apply that in the problems to solve that problems. But here, the theory and coming to the derivation part is included. So mostly you have to concentrate on this second part or the first part related to the branches. Be thorough and be concentrate when you are listening and practice. Then only you'll get this understood, the total convolution and the correlation, the concept of convolution and concept of correlation. Why I'm saying this is strictly you have to learn and learn and learn means this total unit is depends. This total units what we discussed here. It is useful in the coming year, third year. There is another subject is there, digital signal processing. That is application of the signals and system. There, some more examples we have to go for to do the convolution problems. And convolution also there is 2 or 3 types is there to solve the convolution problems, and correlation problems also there 2 or 3 times different ways we have to solve the problems in the correlation also. Follow my dear students. It is only the basic here. If you understood here that this basic, then you can understood the digital signal processing. There is 2 or 3 units is related to these topics. 2 or 3 units are related to these topics, my dear students. Understood. That's why I am strictly saying that you have to see these videos twice and practice twice and twice. Okay, my dear students. Any doubts? Any doubts? Thank you.